In this lecture, there are the last two topics of this lecture series. So firstly, I'm going to briefly talk about the semi-classical analysis of loop quantum gravity. And then the second part, I will talk about some quantum statistics and relates to black hole entropy calculation. Okay, so firstly, semi-classical analysis. Semi-classical states of loop quantum gravity. Okay, so the semi-classical states of loop quantum gravity is very much an analog of coherent state in harmonic oscillator. So in loop quantum gravity, that semi-classical state is also called coherent state. So the idea is very similar to harmonic oscillator. Recall that in harmonic oscillator, you have annihilation operator, right? And the coherent state is just the annihilation, the eigenstate of annihilation operator. And this Z is just the coherent state label, and or the eigenvalue corresponds to the eigenvalue for the annihilation operator. Okay. And this coherent state label so this is a general feature of coherent state, is that the coherent state label is complex. So it is complex. Z equals to x plus IP, right? So we are considering just one-dimensional harmonic oscillator in quantum mechanics, and this is complex, and it is a complex coordinate for of the phase space. So here, because this phase space is really simple, you have just two-dimensional phase space. You have x and p as the coordinate. Well, but the coherent state, it is labeled by the complex coordinate of the phase space. Yeah, because phase space, it is always it's always even dimensional. So in this case, this is just a two-dimension. This is R2 of phase space. So this is, in this case, it's just R2, but R2 is the same as complex plane. Yeah, so you can always use complex coordinate to parameterize the phase space. And the coherent state label, so this is coherent state label, this is always this complex coordinate. Okay, and or another word to say is that the coherent state label, it is a phase space point. Yeah, so so given Z, this is a complex coordinate of the of R2 or complex plane, and given Z, given this number, this complex number, it uniquely fixes a point on the phase space. So the so this coherent state label is actually the phase space point. Okay. And remember this feature. So let's look at loop quantum gravity coherent state. LQG coherent state. Okay. So firstly, let's consider on a single edge. Let's consider on a single edge. So here I just give all the derivation for this coherent state, and for details you can read the book by Thomas Tiemann. Yeah, how to derive it. So here I'm just give you the result of this coherent state, and this is written in this. So on a single edge, so this state is just, it belongs to the Hilbert space on a single edge, which is L2 over SU2. Okay, so this state belongs to this Hilbert space, and clearly it is a square integrable function of holonomy. So this is defined to be summing over J from 0 to infinity, and J is of course half integer. and the sum is 2j plus 1 e to the minus t half. So there's a parameter t, j plus 1 ij h in. Okay, so you can see that, well, this expression is not complicated at all. It's not complicated, and it relates to, firstly, it relates to the chi j. This is the SU2 character in spin j representation. This is SU2 character. Of j representation. Okay. So what is the character? So character is nothing but the trace of the Wigner D matrix. This is just the trace in the representation J of this DJ matrix. So Wigner D matrix is just a matrix element of the representation, and matrix element of the representation matrix, and this character is just taking the trace of that representation matrix. So this is called a character. And so you can see that the coherent state has two labels, just like harmonic oscillator, it has a coherence label Z, and well, for it also has another label which is H bar, right? Coherent state has this state, of course, H bar, and so here this G plays a role similar to this Z for harmonic oscillator, and T plays a role as H bar. So we just write everything. Write all the labels explicitly. Well, here this H, of course, belongs to SU2 because this coherent state is a function of SU2. Well, now what is G? This G is again a complex coordinate of the phase space. So to be explicit, so it's written like this. Okay. Tau A. Now let's consider just still using J to be Ij to be SU2 indices. 2 and then E to the theta J. Okay, so this is a G. So this G, because remember tau is the anti-Hermitian matrix. So tau is minus I. Sigma is a Pauli matrix. So this E to the theta tau J, it is a SU2 group, but this is not. This is not anymore an SU2 group element, but this is a SL2C group element because there's I. This is the prefactor in front. So P and theta, they are always real. So this guy G belongs to SU2 but belongs to SL2C. But we know that SL2C is a complexification. Okay, so firstly, SL2C is a complexification of SU2. So you can see that this is really some kind of complex coordinate. Is a complexification of SU2. Okay, and you can also see it by counting the dimensions. So SL2C, it is complex three-dimensional group. Yeah, so real dimension is 6 dimensions because it's like Lorentz, it's the same as Lorentz group, and same dimension as Lorentz group. And SU2 is has 3 real dimensions. Yeah, so it's SL2C is double dimension of SU2. So yeah, it's consistent with the fact that it is a complexification of SU2. And secondly, this SL2C, according to the manifold, it is from the manifold perspective, it is the same. The manifold of SL2C is T star is a cotangent bundle of SU2, or it is R3 plus S2. Okay. Remember when we talk about the phase space or holonomy flux algebra, of loop quantum gravity, the classical and the classical phase space for loop quantum gravity on a single edge, right, or on the lattice in general. But the lattice is just the phase space tensor product, the cross product of the phase space on the single edge. And this guy, it is exactly the phase space of loop quantum gravity on the single edge. On the edge. Okay, and it contains the coordinate of this phase space is holonomy and flux, and the holonomy belongs to this SU2 part or this S3. You know, SU2, the manifold for SU2 is S3, and flux belongs to this R3. So the coordinate is Pj and holonomy H. Okay, but now this Pj is the same Pj here, right? And this is the Pj, and reflect to the coordinate Pj in the phase space. And here we, on the other hand, this H, I use e to the theta to parameterize this H. So which means I use two coordinates P and theta to parameterize this phase space. Okay, and also I don't want to use H here because H is entry of the function, because I write this function as a function depending on H, and but this holonomy, this guy, this SU2 group element is some part of the G, yeah, which is independent of H. So I don't want to use H to write the SU2 part of G. Okay, so here you can see that this G depends on P and theta. Yeah, P is the flux, and theta or e to the theta, it is the holonomy. So which means that G contains both holonomy and flux. Okay, and it is a complex coordinate of the phase space and parameterize. It's parameterizing the phase space. Of course, it depends on both holonomy and flux. All right. So one remark is that this Pj is not so very more precisely. This Pj is lowercase p. It's different from our previous p. So this lowercase Pj equals to our previous capital Pj divided by a square. So this a square. So I think I have mentioned this a square when we talk about flux. So this a is a length unit. Okay. And for example, you can take a to be just like 1 millimeter or 1 centimeter, whatever, depend on your unit. So then the meaning of this lowercase p is the, because this capital P is of area dimension. The dimension of capital P is like area. So the Pj divided by a square, where a is a unit, it means that so you are measuring this area. You are measuring P by using certain unit. So Pj is the number for this measurement, okay. And therefore this Pj, it is a dimensionless quantity. So this is dimensionless flux. Dimensionless flux. Okay. Because Pj is dimensionless, you can put on the exponential. Yeah, you can put this lowercase p on the exponential, and to define exponential minus ip tau j, and combine with e to the theta holonomy to get a complex group element, or G belongs to SL2C, and this complex group element, it contains both information of P and theta, and it parameterizes the as a complex coordinate, parameterize the SL2C and parameterize the phase space of L2G. Okay, so this is the complex coordinate. And similar to harmonic oscillator, so suppose you you know the number, the complex number z, you just extract the real part and complex part, the imaginary part, then you get x and p, yeah? And you know where you are at the phase space. And similarly here, suppose you know g, and you can just make a polar decomposition of this SL2C, then you can uniquely decompose into decompose g into this form. Then you can extract p and theta, yeah, and for p and holonomic, yeah? And you know where you are in the phase space. So therefore, the coherent state, it is labeled by a point in the phase space. Yeah. In other words, it's labeled by the complex coordinate in the phase space, or it's labeled by a point in the phase space. Okay, and the dependence on G is entering this entering this character. So because this character is just analytic function of SU2, yeah, it is character. Firstly, it is the SU2 function because this is trace of the Wigner D matrix. Wigner D matrix is a function of SU2. And secondly, this character is the analytic function. Yeah? It is analytic function. So you can always analytically continue this function from SU2 to SL2C, because this is just some polynomial of the matrix elements of SU2 matrix, two-dimensional 2x2 SU2 matrices. Yeah? So character is just some polynomial of those matrix elements. And then, of course, you can plug in analytically continue this function to SL2C. Yeah? Just replace 2x2 SU2 matrix element by SL2C matrix element. And now this entering characters is G times H inverse. In general, well, G is SL2C and H is still SU2. Okay, so this just some basic introduction for this SU2 coherent state. And then this is the coherent state on a single edge. And easily you can generalize the coherent state on the entire graph, gamma on entire lattice, and you just make the product. So this is the coherent state on the entire lattice. It depends on it's a function depending on all holonomies on the lattice. Is equals to, it's just to make a product of E gamma T GE H. So on every edge you have one coherent state and you just make product. Okay? And this quantity, this state belongs to H gamma 0. So it is not gauge invariant yet. It is not yet gauge invariant because you just have a single edge coherent state and you just make a product. Yeah? And you didn't, well, this wave function is not gauge invariant. So it belongs to H gamma 0. It is not SU2 gauge invariant. So people usually call this non-gauge invariant coherent state. And you can also define gauge invariant coherent state. SU2 gauge invariant coherent state. By the way, the non-gauge invariant coherent state, because you make a product of all the over all the edges on gamma. So this is labeled by vector G. It means that at every edge you have a G. Yeah. So this vector G, it is complex coordinate of T star SU2 over all edges. To the power of E gamma, the total number. So this is total number of edges. Okay. Yeah. So on every edge you have a G. You have one G. So Now you can define the gauge invariant coherent state. So this is written as capital Psi T and G, and this G in the square bracket, it means that it is not a coordinate of this guy, because this is a non-gauge invariant phase space. So the physical, well, the gauge invariant physical gauge invariant phase space is this phase space modulo gauge action, gauge orbit. Yeah, and now this G, of course, is not gauge invariant, and then the gauge orbit act on G, well, it give you a orbit. The gauge transformation act on G give you an orbit, and this square bracket G, it is a gauge orbit. So, or you can view this is a gauge equivalent class. So this is a gauge orbit. Gauge orbit. Starting from, well, at G. So given a phase space point labeled by G, and you make gauge transformation, and it generates gauge orbit. And this square bracket G, it is the gauge orbit. And so the label of this gauge invariant coherent state, it is really the gauge orbit, not just a single phase space point. So this is given by a group averaging, the group action. It is actually the group action of this wave function, and then you integrate over all possible group actions, and then the result, it is gauge invariant. So this is a hard integral of all the gauge transformations on at vertices. Well, let me use U to be the gauge transformation. So this is integrate over SU2 to the power all the vertices, number of vertices, okay? And integrating the gauge transformation of psi. Yeah. So in the end, this gauge transformation transform to the gauge transformation of the coherent state label. Okay. So this is the group averaging. And what is this coherent state label? HG transformed by H. This is just the ordinary, similar to the gauge transformation for holonomy. Okay. So this can be derived from the definition of coherent state. And suppose you make a gauge transformation for H, and because this chi is just a trace, so the gauge transformation of H transform to the gauge transformation of G. Okay, because this chi is a trace of the matrix. Okay, and then you get the gauge transformation for the coherent state label G, and then you integrate over. Sorry, so this is not H, this is U. And now you integrate over all the gauge transformations, and you get a gauge invariant state. And clearly, this gauge invariant coherent state is labeled by the gauge orbit of G, not by G itself. Okay, so this is the semi-classical state for loop quantum gravity. And now let me tell you about why we call it semi-classical, because the reason is that they have several interesting semi-classical properties. So for simplicity, let's only talk about the coherent state on the single edge, the property for coherent state on the single edge, and those properties can be generalized to other to coherent state on graphs. Okay, properties of G on the single edge. So let's say GE. All right. So firstly, it has semiclassical property, semiclassicality. Okay. So if you compute, so given a coherent state on the edge, you can compute the expectation value of holonomy operators and flux operators. Okay. So it is just a state in the Hilbert space, and then you can compute the holonomy operators, the expectation value of the holonomy operator. Okay. And again, associated with the same E. Okay, and the result is very simple. So it is just the classical expression of holonomy plus order T. Oh, so sorry, probably I haven't tell you what is T yet. T is just H bar, so I gave you an idea, but more precisely, T is LP squared divided by A squared. Okay. So this is the dimensionless LP, dimensionless Planck length square, because LP square is clearly of dimension area, and divided by A square, A is a unit. Okay, A is a unit, and so T is just T just measures the value of LP square in this unit. Yeah, so T is a dimensionless. Is a dimensionless. Dimensionless semiclassicality parameter. Okay, semiclassicality parameter. Okay, so well, it is semiclassicality parameter. It means that the semiclassical limit, so H bar goes to 0. Here, it's equivalent to T goes to 0. Okay, so T goes to 0. It means that, well, LP, you can neglect the effect of LP, right? And it means LP is much smaller than your unit A. So you are fixing a macroscopic unit like 1 millimeter, yeah, and LP is much smaller than 1 millimeter. Yeah, then you can take. It means that you take T goes to 0. It's a semiclassical limit. Well, T plays the same role as H bar in Dupont gravity. Okay, so the expectation value of a holonomy operator just give you holonomy plus order T. Okay, so and this holonomy, it is the holonomy coming from G. Okay, because remember this G E equals to E to the minus I PE. Okay, half E to the theta E J tau J half. Okay. Yeah, and this so it means that you're taking the expectation value of holonomy operator using coherent state. It just extract the holonomy part, the SU2 part of this G, yeah? And this is the same as here. And it just it means that the expectation value of holonomy operator is just the holonomy at the phase space where this coherent state is labeled. And similarly, the flux operator, expectation value of flux operator, small p. Okay. This is just give you the flux the flux for this coming from G. Okay. And so this flux is the same flux here. Okay, so It means you take the expectation value of the flux operator. The result it just extract the flux at the phase wave point where this coherent state is labeled. Yeah, and of course, this expression order ignore the higher order corrections in H bar. So it means that in the semiclassical limit, the expectation value give you